Hello and welcome to the course of Advanced Strength of Material. I am Soumobroto Chakraborty. So this is your module 1, lecture 1. The title is Strain Energy, Theory and Expression under Gradual Loading. So first we will see the lecture objective. In this lecture, our lecture objective is first to revise the prerequisite. So in the syllabus there is some prerequisite because this subject is the advanced version of the strength of material you have studied in last semester. So under this we will revise some prerequisite. We will revise some prerequisite to achieve this objective. Then to understand the meaning of the strain energy. Thirdly, to introspect the concept of resilience, prove resilience and modulus of resilience. And fourthly, to derive an expression for strain energy of axially loaded member under gradual loading. And fifth, to understand the methodology for simple numerical problems. So this is our lecture objective. Now let's start with revision of the prerequisite. So in prerequisite, the basic strength of material we have studied. The first thing in the strength of material that we should know that what is stress. So stress, what is stress? Stress, it is the internal resistance per unit area developed in a body when some external load tends to deform the body from its original position. That means this is well known to us. This is completely well known to us. When there is a body, if this is a body, when this body is loaded externally means it is tends to deform for the action of the external force P Newton. For the action of the external force P Newton. What happened? This body tends to elongate. So this elongation, resistance to this elongation per unit area is known as stress. This is well known to us. The unit of stress Newton per meter square or Pascal. So stresses can be normal or shear stress. So normal or shear stress. So normal stress can be further defined as tensile and compressive in nature. Similarly, the other type of stress is shear stress. So this is an example. This example is an example of the tensile stress. See this concept of normal stress, tensile stress and compressive stress, shear stress, these are well taught in the previous semester in strength of material paper. So now we will move to the another term that is well known to us from from the previous semester, that is strain. What is strain? Strain is the ratio of the deformation to its original position is known as strain. Strain, it is a unitless quantity. It is an unitless quantity. Strain can be longitudinal. Longitudinal strain means this is del L by L. It is longitudinal strain. That means change in length by length is known as longitudinal strain. Similarly, lateral strain for circular rod can be del D by D. That means change in diameter by original diameter. This is longitudinal strain, lateral strain. Similarly, for normal stress and shear strain, normal lateral strain, this longitudinal and lateral strain developed for normal stress, and for similarly shear strain Similarly, shear strain, that is del theta by theta, it is developed for shear strain. Okay. Now another shear strain. Now what is elasticity? Elasticity is a property of a bodies. Elasticity is a property of bodies by virtue of which they return to its original shape. They return to its original shape means when the body is loaded externally, the body is tends to elongate. So if there is some elongation, then there is some strain. So when then there is some strain when the load is removed. When the load is removed, that means when this P load is removed, when this P load is removed, then the body will move to its original shape. So that means that original shape means this move it to the original shape. This property of moving back to its original shape when the load is removed is known as elasticity. So this is also well taught in previous semester, and according to Hooke's law, stress is proportional to the strain. We know that stress is proportional to the strain, and the ratio of between them is known as Young's modulus. A ratio between them is known as Young's modulus or modulus of elasticity. That means if sigma is the stress and epsilon is the strain, then ratio between them is constant. And that constant is known as modulus of elasticity or Young's modulus. So this is we know from the Hooke's law. So these are the some prerequisites and which are important for the study of the strain energy. So we have revised all of them. So I guess there is no problem here. So and here one term is here according to Hooke's law. So this Hooke's law is applicable only within the elastic limit. Elastic limit means, see what elasticity means. Elasticity means the property by virtue of which it returns to its original shape, by virtue of which body returns to its original shape when the external load is removed. So now this is the limit. Elastic limit means the limit up to which this Hooke's law, this proportionality law is valid. So if this is the stress strain curve, sigma versus epsilon curve, this is the stress strain curve, and this limit, if this is B, so from A to B, this is from A to B, this is known as from A to B is known as elastic limit. From A to B is the elastic limit. That means in the elastic limit only the Hooke's law is applicable. So this all of this we have studied in the last semester only. Now we will proceed further. Next we will come to our topic, that is strain energy. See, strain energy means, so by now what we know that when a force is applied, when a body is loaded, that means when a force is applied in a body, if this is a body, if a force is applied, this P force is applied, then this force tends to deform the body. So due to the deformation, due to the tendency to be deformed, there one internal resistance will occur on the body. This internal resistance work on the body, do the work on the body. So some energy is stored due to the process of deformation. Due to the process of deformation, this energy is known as strain energy. Now we will see the definition. When a body is subjected to, see, loading can be gradual, that means we are increasing the load gradually with time, and or impact, at an impact, or by sudden loading, whole load at a sudden time, or shock loading. That means when a body is subjected to gradual impact or sudden loading, the body deforms. The body deforms. This is the basic knowledge that when the external load is applied, the body deforms, and due to that deformation, work is done upon the body. Work is done upon it under the elastic limit. This work done due to straining under the elastic limit, this work done due to straining or work done due to deforming is stored in the body. This work done or energy stored in the body is known as strain energy. This is the definition, this is the engineering definition of the strain energy. What is this? When a body is subjected to gradual impact or sudden loading, the body deforms and work is done upon it under the elastic limit. This work done due to straining is stored in the body, and this work done or energy stored in the body is known as strain energy. That means in another way we can say that energy stored in a body during straining or during deformation process is known as strain energy. That means work done or the energy stored. Both, that means work done or the energy, that means work done or the energy stored. Both are same, and both of them means strain energy. Okay. Now see. Now three important definition that we should know, or three important concepts that we should know. That one is resilience, proof resilience, and modulus of resilience. So what is resilience? Resilience is the total strain energy. Total strain energy stored in a body is known as resilience. So total strain energy, total whole strain energy, total strain energy is known as resilience. That is capacity of a standard body to doing work when strain is removed is known as strain energy. So if sigma is the total stress developed and E is the Young's modulus and V is the volume of the body, then the total strain energy is equal to U sigma square by 2E into V. So sigma is the total stress, sigma is the stress, sigma is the stress, and V is the volume of the body. V is the volume. So V is the volume. So from here we can say that resilience is equal to resilience U is equal to, this is resilience U is equal to sigma square by 2E into V. Now secondly, proof resilience. Proof resilience means the maximum, proof resilience means maximum strain energy stored in a body is known as proof resilience. Maximum strain energy, that means quantity of the strain energy that is stored body when the body is strained up to elastic limit, when the body is strained up to elastic limit. That means this sigma E is the stress at stress at stress sorry this sigma E this sigma E is the stress at elastic limit. Stress at elastic limit. Okay, so sigma is the stress at elastic limit. So maximum strain energy stored, that means the strain energy stored by in a body when the body is strained up to elastic limit. When up to elastic limit, then maximum strain energy is stored. Then this is known as proof resilience, or the value is equal to up or u proof resilience is equal to sigma E square by 2e into v. Now modulus of resilience, the maximum energy stored in a body per unit volume. Maximum energy stored per unit volume is known as modulus of resilience. So modulus of resilience can be written as proof resilience per unit volume. That is small u is equal to 2 sigma E square by 2e. So these are the value sigma E square by 2e. So these are the important definition. These definitions are very important in MCQ and in question. These terms are heavily asked, and in the later section we will see the application of these terms. So another time, the total strain energy stored in a body is known as resilience, maximum strain energy stored in a body is known as proof resilience, and maximum strain energy per unit volume is known as modulus of resilience. So it's so simple that total strain energy is equal to resilience maximum strain energy is equal to proof resilience and maximum strain energy per unit volume is equal to mod of resilience. Okay, so now next we will see the expression for gradually applied load. In gradually applied load means the load is 0 at time t0, or and then it is applied at small amount at a time. So when the load is applied at small amount at a time, from starting from 0 to some amount, that is the extension or deformation is also change as the load changes, as the load changes. So see, we will see the expression for that. So for that, let us consider a bar of length L placed vertically at one, and one end is attached with the ceiling. See this picture. See this picture here. A bar of length L, it is attached with the ceiling. Now P is the gradually applied load. Now let P is the gradually applied load, L length of the bar, A is the cross section of the bar, del L is the deflection produced in the bar. This deflection is produced in the bar due to the externally applied load L, and sigma is the axial stress induced in the bar. It may be tensile or compressive depending upon the nature of the load, and E is the modulus of elasticity. Here I missed one term, that is epsilon. It is strain. It is equal to strain. Strain due to load. Strain due to load P. So now we will see that the loading diagram, due to this loading diagram, the load deformation diagram looks like this. As the load increases, deformation increases from 0 to L, and similarly the resistance, as the deformation increases or the tendency of deformation increases, resistance is also increases in DL direction with the deformation. So this curve, this A is the load deformation diagram and B is the load resistance deformation diagram. Now work done on the bar is work done on the bar. Now we want to derive the strain energy. So for strain energy, we need to derive the energy stored. So for that we have to know the work done on the bar. So work done on the bar is area under the load deformation curve, that is half P into DLC. If this is P and the area of this shaded area, so this shaded area triangle is half base into height, the area will be half base is del L, and height, that is P. So area under the load deformation diagram is half P into dl. Now for energy work stored in the bar, that is the resistance in the bar. So that is area under the resistance deformation diagram. Here also see area under the resistance deformation diagram. So area of this shaded area, area of this will be half into height is R, and this is base is dl. So this is the area. So area of the resistance deformation diagram will be half R into dl. Now we know R is equal to, R or resistance can be written as sigma into A. R resistance can be written as sigma into A. So why the resistance can be written as sigma into A? Because remember the definition of sigma, or definition of the stress is equal to internal resistance, or R per unit area. So from that we can write R is equal to R is equal to sigma into A. So putting this value R is equal to sigma into A here, putting this R is equal to sigma into A here, we get work stored in a bar is equal to half into sigma into A into dl. Now see, we know that work done is always is equal to work stored due to conservation of energy. So we can write P dl into P half P del L is equal to half sigma into A into del L. Now del L cancel out, half cancel out, we got P is equal to sigma into A, that means sigma is equal to P by A. This is the stress due to gradual loading. So sigma is equal to P by A is the stress due to gradual loading. This is an important observation from the expression of the strain energy. Now we are mainly want to find out the strain energy. So strain energy is equal to, strain energy means energy stored in the body. So what is the energy stored in the body? Energy stored in the body we have derived right now. Energy stored in the body is half the R into dl. So energy stored in the strain energy can be written as half R into del L. Now this R can be written as like this, sigma into A. R can be written as sigma into A. So putting this value sigma into A, we got half sigma into A into dl. Now sigma into A into dl. Now see dl. Now dl can be written as this. dl can be written as epsilon into L, because epsilon is the stress, this epsilon is the strain is equal to original length deformation is equal to original length into strain. So epsilon into L. So we can write this. Now again epsilon can be written as epsilon from here, epsilon can be written as epsilon is equal to sigma by E. So putting this value here in place of epsilon, we got half sigma A epsilon by E into L. So simplifying this, we got sigma square by 2E into AL. Now AL can be written as V, AL can be written as volume of the body or V. So U is equal to epsilon, U is equal to sigma square by 2E into V. This is the strain energy this is the expression of the strain energy due to gradual loading. Now this derivation along with these two expression, that means this strain energy expression and this stress expression for gradual loading, these things are important. This derivation is also important, and right now we will see some one example or simple problem. So these problems are also important. These problems are mainly based on only the topic we have discussed so far, that is strain energy developed due to gradual loading. See, the question says a tensile load of 60 kilonewton is gradually applied to a circular bar of 4 centimeter diameter and 10 meter long. What will be the stretch in the rod? If E is equal to 1 into 10 to the power 5 Newton per millimeter square? So now we will see the solution. So first, what is given? Given is, so first what is given? Given is load is equal to 60 kilonewton. That means load is equal to 60 kilonewton. 60 kilonewton means 60 into 10 to the 3 Newton into 10 to the power 3 Newton. Now area is equal to, for area for circular area, circle area. Why circle? Because the rod is circular area. Why circular? Because the rod is circular or bar is circular. So that is pi by 4 d square. Now d is equal to, we got d is equal to 4 centimeter, that means 40 millimeter. So we got the area as 1256.63 millimeter square. Now length is equal to 10 meter, that means 0.01 mm. Now stress, we have seen in the formula that we have seen, or we have derived in that formula, that stress in gradual loading is equal to load by area, that gives us P by A, that gives us 60,000 by 1253.63, that is 46.74 Newton per millimeter square. This is stress. We need to find out the stretch. Stretch means the elongation. So elongation is equal to, so elongation, we need to find out the elongation. How the elongation should be find out? Elongation should be find out like, elongation mean, see, elongation means del L. We need to find out del L. So del L can be written as epsilon by epsilon into L, or epsilon into L, or epsilon can be written as sigma by E. So stretch can be written as sigma L by E. Stretch can be written as, so stretch can be taken as sigma L by E. Now from here, putting the values from here, now from here, putting the values of sigma, putting the values of sigma and putting the values of sigma and L and E, we got stretch is equal to 4.77 mm. So this will be the, so this 4.77 mm will be the answer. Okay, so this type of simple problem will come in exam also. So we will see to another simple problem. So these two problem, this problem, so this problem you will practice it, try to do it at your home. So here what is given, it is given as the tensile load is 100 kilonewton and the rectangular bar, and the rectangular bar of dimension 2 semi and 4 semi length, for dimension 2 cross 4 centimeter, and the length is of 5 meter. What will be the strain energy? Strain energy. So we need to find out the strain energy. So formula for strain energy is, we have just derived the formula for strain energy is U square is equal to, U is equal to sigma square by 2e into v, right? So using this formula only, this can be derived. Similarly, for this problem, this is the same problem as the first problem, but here we need to find out the strain energy absorbed. So that strain energy absorbed can be given by U is equal to sigma square by 2e into v. Okay, so from this we can find out the strain energy, from this we can find out the strain energy. So these two problems we will do you will do at home, and in live class we will discuss about these two problems also. Thank you. This is for today. Thank you. Hope you enjoyed the lecture, and if you have any problem, then please feel free to contact with me.